Welcome everyone. Today we are going to explore one of the fundamental data structures in computer science, hash table. This is part 1 of our lecture on hash tables, where we will cover the basics, including the concept of hashing, the operations associated with hash tables, and how they enable fast data access. Okay, here we'll see the concept of the hash table entity or abstract data type. A hash table is essentially a table of elements where each element has an associated key. The key is used as an identifier, allowing us to store and retrieve data efficiently. The efficiency of a hash table is largely due to the use of a hash function. This function takes a key as input and returns an index corresponding to a position in the table. This index is where the element associated with that key will be stored. So the table of elements itself represents the data set that the hash table acts upon. So by leveraging the hash function, the hash table enables quick access to these elements, making it a powerful tool for data storage and retrieval. Now let's go over the core operations associated with a hash table entity. First, we have insert. This operation adds a new element to the hash table. The hash function calculates the position where the element should be stored based on its key. Then retrieve. This operation allows us to find and retrieve an element from the table using its key. The hash function is again used to quickly locate the element. Next, we have remove. With this operation, we can delete an element from the hash table. Removing an element might require handling to avoid leaving gaps, depending on the hash table's collision resolution strategy. Next, we have update. This allows us to modify an existing element in the table. Using the key, we locate the element and then update it with new data. Then finally, there's an operation to clear all elements from the hash table, effectively resetting it. So these operations illustrate why hash tables are so useful. They offer efficient direct access to elements, which makes them highly effective for various applications, from database indexing to caching. Now, one of the main reasons hash tables are so popular is their ability to provide fast search capabilities. A hash table uses a hash function which takes the key value of an element and calculates an index that corresponds to its position in an array. This approach allows us to perform search operations in constant time, or theta 1 on average. This means that regardless of the number of elements in the table, the time taken to find an element remains approximately the same. The key to this efficiency is the hash function itself. By mapping each key to a unique position or nearly unique, depending on collisions, the hash function ensures that elements can be accessed directly without the need to search through the entire data set. Now, let's discuss the key component that makes hash tables so effective, which is the hash function. The hash function is a function that takes an input called a key value and generates an output, which is the index of an array where the element is stored. This index tells us exactly where to look for the element, allowing for quick access. For example, let's consider a simple hash function, hk equal to k and then 100. So in this case, the key k is divided by 100, and the remainder of that division gives us the index. This method is common for integer keys, as it ensures that the index stays within the table's bounds. The choice of hash function is crucial for the hash table's performance. A good hash function distributes keys uniformly across the table, which helps prevent collisions. A situation where two keys map to the same index. In upcoming slide, we'll discuss strategies to handle such cases. Now let's go through a practical example to see how a hash function works in a hash table. Suppose our hash function is defined as hk equal to k 100. Now this function takes a key, divides it by 100 and uses the remainder as the index in the hash table. Now let's say we want to search for an object with the key value of 214. We input this key into our hash function. So k equal to 214. The calculation 214 divided by 100 gives us a result of 14. 14 is the remainder. Now this means the object with the key 214 should be stored at index 14 in our hash table. When we search for this object, the hash function quickly directs us to index 14, which allows us to retrieve it in constant time b theta 1. Now this example illustrates the power of hash function in enabling fast data retrieval, as we don't need to search through the entire array, just the specific location calculated by the function. Now let's look at how an element is inserted into a hash table using a hash function. To insert an element, we apply the hash function to its key. In this example, our hash function is hk equal to k divided by 100. Now which calculates an index based on the key. Suppose we want to insert an element with a key value of 214. By plugging this key into our hash function, we get 214 divided by 100, which gives an index of 14. Therefore, we place this element in index 14 of the array. This insertion is performed in constant time or theta 1 because the hash function directly maps the key to its position in the array, allowing us to bypass the need to search for a location. This efficiency is what makes hash tables particularly powerful for fast data storage and retrieval. Now let's take a step back and look at the big picture. Imagine we have millions of key values and we need to search for a specific item like a part number. If we were to use a regular array or a linked list for this search, it would take a long time, potentially requiring hundreds of thousands of comparisons on average. For example, if we had 1 million keys, we might need to search through like 5 lakh of them to find the one we are looking for. With a hash table, however, we avoid this lengthy search process. Instead of going through each element, we use a hash function that directly provides us with the index where the key is stored in the array. This allows us to locate or insert an element in constant time, making hash tables highly efficient, especially for large data sets. Now let's talk about collisions, a common challenge in hash tables. Now consider our hash function hk equal to k100. This function maps keys to indexes within a range of 0 to 99. Now suppose we have a key value of 393. Then when we apply our hash function, this gives us an index of 93. So the object with key 393 is stored at index 93. Later, we try to insert another object with a key value of 193. Again, 193 divided by 100 results in index 93. However, index 93 is already occupied by the object with this key 393. Now, in this situation where two keys map to the same index is called a collision. Now, handling collisions effectively is essential for maintaining the efficiency of a hash table. In upcoming slide, we'll see how to manage how are collisions resolved. Now that we understand what is collisions, we'll see how to resolve them. We have a common there are some ways, but most common way is chaining. In chaining, instead of storing a single object at index or each index, we use a linked list. Each index in the hash table points to the head of a linked list where all elements that hash to that index are stored. This way, if multiple keys map to the same index, we can simply add each new object to the front of the linked list at that index. To insert an element, we use the hash function to find the index, and then we insert the object into the linked list at that position. Typically, these linked lists are quite short, so even if a collision occurs, the search time within the linked list is relatively quick. So when searching for an element, we apply the hash function to determine the index, and then we search through the linked list at that index. This approach is still much faster than searching through the entire dataset, especially in large hash tables. So chaining is an effective way to handle collisions, allowing the hash table to maintain efficient performance even when multiple elements share the same index. Now we'll see an example here. Example using chaining. Here we have a hash table that starts empty with each index containing a pointer to a linked list. Initially, each pointer is set to null, indicating that there are no elements stored yet. So our hash function in this example is hkk7, which means that any key value will be mapped to an index by calculating the remainder when the key is divided by 7. This results in indexes from 0 to 6. As we add elements to the hash table, we'll use this hash function to determine their position. If multiple elements map to the same index, we'll insert them into the linked list at that index, creating a chain of elements. So this linked list setup allows us to handle collisions effectively by keeping all elements with the same hash index together. Here, first, if you see, we are inserting object with key 31. So insert object with key 31. If we do that, our index will be 3. Now we inserted 31 on number 3 index. If you look at here, we inserted this 31, the value key, on index 3. Now the whole object is stored, but only the key value is shown. Next, we'll insert key 9. Here the remainder is 2, so we'll save it on index 2. So 9 is added to index 2. Okay, so now if you look at the third one, we will insert key 36. Now 36 by 7 is the we have the remainder 1. Now we'll insert 36 into index 1 here, right this way. Now if you look at here, the first one we inserted 31 into index 3, then the second one 9 we inserted into 2, and then on the third one the remainder is 1, so we inserted on index 1. So this is how we insert values in a hash function. Now let's look at the fourth one. We'll insert key value 42 here. Now 42 by 7 is 0, so we don't have any remainder, so it will go to 0. So we inserted 42 into 0. Then you see here, now we'll insert 46. 46 by 7 is 4, the remainder is 4, so we'll add 46 into the index 4 here, like that. All right, now we'll insert object with key 20. So if you see, 20 divided by 7 is 6, so the remainder is 6, so it will be added to index 6 here. If you see, 20 is added to index 6. Now we want to insert object 2, key 2. Now 2 by 7 is 2. There is no other remainder. Now there is a collision now, because we already have 9 on index 2. Now how can we overlap or overwrite it? If we overwrite it, the 9 will be gone, and then when we will search 9, we can find 9. Now that's because of that, now we will use the chaining system to add a linked list here on the same index. this like I said, key 2 is just inserted in the linked list. The insert function of linked list inserts a new element at the beginning of the list. So you will see here that will move, the 9 will move, and then 2 is inserted here right away. So always remember, when you add a new value, it always insert the new value at the beginning of the linked list. So the previous value has to move right so that you can insert the new value. So that is how we can do the chaining. If you look at here, the address is pointing to the next value 9 from 2. So that's how linked list work. So we already learned about linked list in previous lecture. I hope you already know how linked list work. So let's move on to this example. Now we want to insert key 24. Now 24 by 7 is 3. Now there is a collision again. Now we'll move 31 here, and then we'll insert 24 on index 3. Next we have so we want to we did the insertion, and then now we want to find the object with key 9. Now here, if you look at this example, we up until now we were adding value to our hash table using this hash function. Now we will find the key. We want to find the key from the hash table. So we want to search for a key inside the hash table. Now how to do that? Let's see how to do that. Now you will see we want to find the object with key 9. Now 9 divided by 7 is 2. So we will go to index 2 now. Here this one is the index T. We search this linked list for the object with 9. Now here we'll search. Remember, the whole object is stored, only the key is shown. So here we'll search, does this object contain key 9? We'll see if first one, what is in the beginning of the linked list, we'll see if this one contains the object key 9. No, this one is not 9. So we will then move to next object, this one. So does this object contain key 9? Yes, we found it, and then it will return the object. So it is much easier, way much easier than going through the whole data set if it's a large data set to find a key using a hash function or in a hash table. So that's why it's a very fast approaching. And then if you have a very huge big data set, you can just quickly find any key from that hash table like this way, in this way. Even if you have linked list on several indexes, if you have multiple values in using linked list in several indexes, but still you can find that more quickly than using the normal traditional search function. That's why hash tables are so popular. So I hope you all understand the whole example, because I made it very detail so that you will know how things works, and then you won't. I don't see any. I don't want you to have difficulty understanding these things, so that because these things are very important, and you will get questions on your exam about these things, or even if you're in your homework. So I want you to learn and understand the whole thing. Now let's discuss an important concept in hashing known as uniform hashing. Now, uniform hashing occurs when elements are spread evenly or almost evenly across all the indexes in a hash table. This even distribution helps prevent clustering where too many elements end up at the same index, which would otherwise lead to long chains in chaining or access probing in open addressing. If we achieve uniform hashing, the number of elements at any given index is kept low, often just a small constant. This ensures that searches can be done in constant time theta 1, maintaining the efficiency that hash tables are known for. The hash function itself plays a crucial role in achieving uniform hashing. A well-designed hash function will distribute keys evenly across the table, minimizing collisions and allowing the table to operate optimally. However, if the hash function is poorly chosen, it can lead to uneven distributions and reduce performance. So in summary, we can say uniform hashing is ideal for maximizing hash table performance, and the choice of hash function is key to making it possible. Now, here, after discussing the importance of a well-designed hash function, let's look at an examples of bad hash functions that can lead to poor performance in a hash table. So if we consider a hash function like hk equal to 5, this function always returns 5. Regardless of the input key, this is clearly ineffective because it would direct every key to the same index, creating a massive collision at index 5 and defeating the purpose of using a hash table. So you have to choose something that will create different values or different indexes. Another example is hk equal to k divided by 100. While this may seem reasonable at first glance, it can be problematic if there is meaning embedded in parts of the key. For example, if the key represents an employee ID where the last 2 digits represent the state of birth, then using this divided 100 might cause employees from the same state to hash to the same values, leading to clusters of entries at certain indexes. So a bad hash function doesn't distribute keys uniformly across the table, leading to collisions and reduced efficiency. When designing or choosing a hash function, it's essential to ensure it avoids patterns in the data that could lead to uneven distribution. Now, let's wrap up with a look at what makes an ideal hash function for achieving uniform hashing. One of the key factors is the hash table size, which should ideally be a prime number. Using a prime number for the table size helps in distributing keys more evenly, as it reduces the chances of patterns in the key values, creating clusters at specific indexes. However, it's also important that the prime number chosen is not too close to a power of 2. For example, while 31 is a prime number, it's close to 2 to the power 5. Which might lead to patterns if the keys themselves have binary structures. Instead, a number like 97 is a better choice because it's not near any power of 2 and is also prime, leading to a more uniform distribution. An example of a good hash function using this approach might be k divided by 97. By choosing a prime modulus that's well suited for the data and table size, this hash function can help spread keys uniformly, minimizing collisions and improving overall efficiency. Now, hash functions can also be designed for keys that are strings, not just numbers. Let's take a look at an example. Here, we initialize an integer variable sum to 0. We then iterate through each character in the string, adding its ASCII value to sum. ASCII means ASCII. That's the term we use. It's called as ASCII value to sum. Then once we have the total sum of the ASCII values, we use the modulus operation with the prime number, in this case 97, to determine the index in the hash table. Now we start with integer sum equal to 0 to initialize our sum. The for loop iterates over each character in the string, represented by string I, and adds its ASCII value to sum. Finally, hash index equal to sum divided by 97 calculates the index by taking sum modulo 97. This approach ensures that the same string will constantly hash to the same index, allowing us to handle string keys in our hash table. However, more sophisticated hash functions such as polynomial rolling hash are often used to reduce the risk of collisions with string keys, especially when dealing with large data sets. Now, let's discuss the trade-off between speed and memory conservation in hash tables. Speed in hash tables is primarily achieved by reducing the number of collisions. Fewer collisions mean that we can locate elements faster, since each index in the hash table ideally has only one or very few elements. This allows us to find the desired element quickly without having to search through long chains or conduct multiple probes. Now, in an ideal scenario with no collisions, a search is extremely fast because the first element we check at the calculated index is the one we need. So, to maximize speed, the hash table size should be larger than the number of keys stored. This reduces the likelihood of collisions by providing more available indexes, which increases efficiency. However, this approach requires more memory, as we are allocating extra space that might not always be filled. So, in summary, the balance between speed and memory conservation depends on the application's requirement. For scenarios where performance is critical, such as in real-time systems, a larger hash table might be preferable, while in memory-limited environments, a smaller hash table with some trade-off in speed may be more practical. Now, we'll see So, designing an effective hash table involves balancing the requirements of speed and memory conservation. The priorities here will depend on the specific application and its constraints. Now, the first step in hash table design is to decide which aspects, speed or memory conservation, is more important for the application. In high performance applications where speed is crucial, we might be willing to allocate more memory to minimize collisions and achieve faster access times. On the other hand, in memory constrained environments, we may need to prioritize more efficiency, even if it means accepting some performance trade offs. After establishing priorities, the next step is to choose an appropriate table size. The size should be large enough to work effectively with a well designed hash table or hash function. Which will allow for uniform distribution of elements and minimizing collisions. So we need a very well designed hash function for that. This helps strike a balance between achieving speed and conserving memory. So, in summary, we can say hash table design is about finding the right configuration of hash function and table size that meets the application's specific needs while maintaining optimal performance. So, your hash function has to be strong enough to avoid collision that will give you more uniform distribution of elements. Okay, now here let's explore the concept of an ideal hash table. Here we aim to have no collisions at all. Is it possible to design a hash function that guarantees this? In specific cases, yes. For example, consider a simple hash function like hk equal to k, where each key is directly used as the index. If each key is unique, then each index produced by hk will be also unique, ensuring no collisions. So you have to be your key has to be unique. Let's say we have 300 employees, each with a unique 4-digit ID. If we set up a hash table with a size of 10,000 using the employee ID as the direct index, we achieve an ideal setup where each employee's record is stored at a unique index. This provides the best possible speed because there's no need for any collision handling. Every element is directly accessible. However, this approach is only feasible in cases where keys are guaranteed to be unique. So, in general applications with arbitrary data, achieving this level of uniqueness is challenging. So we rely on well-designed hash functions to minimize rather than eliminate collisions. Okay, so let's talk about implementing a hash table, specifically one that uses linked list or chaining to handle collisions. In this approach, each index in the hash table points to a linked list. When multiple keys map to the same index, each key value pair is added to the list at that index. This method ensures that the hash table doesn't become full, as each index can hold multiple items through chaining. So without chaining, the hash table would need additional strategies to handle situations where all spots could potentially be filled. However, in the special case of an ideal hash table, as discussed in the previous slide, where every key is unique and maps to its own unique index, we wouldn't need chaining or even a hash table structure. In such cases, a simple array would sufficient since each element has a unique position. But in most real world scenarios, it's not very, all the data is not unique, it is not predictable, and chaining provides a flexible way to manage collisions effectively in a hash table. In many cases, it's advantageous to allow flexibility in the choice of hash function when implementing a hash table. Instead of writing the hash function ourselves, we leave it to the client to define the specific hash function they would like to use. This way, the client can tailor the hash function to meet their specific data requirements or constraints. Once the client has defined their custom hash function, they can pass it as a parameter to the constructor of the hash table class. This approach is often implemented using function pointers, which allow the hash table to use the client's hash function dynamically. So by making the hash function an adjustable component, we ensure that the hash table is more versatile and can be optimized for various use cases, whether it's dealing with numerical, string, or even complex data types. So that's all for today's lecture. This is part 1, where we learned the basics and how hash table works, and how to design, or what is the ideal hash table functions, or how to implement hash function. These things we learned about that, and then we'll move forward more advanced, and we'll learn more about hash tables in our part 2 in next lecture. Thank you.